and also analyze the problems of the previous day contests. So usually we'll have 3 hours of this, and I think our first hour and a half will be devoted to analyzing the problems. Well, it actually depends on how fast we will be able to move on from these problems. And then we are going to have a small break and then some lecture. So actually, I have created a small questionnaire. I do not know if you received it. Have you received questionnaire? Yes. Okay. So today's topic is Cartesian tree, or also known as trip, or also known as rope. But for the next days, I'm going to choose topic looking at this questionnaire, because I actually do not have like good idea of what is your real level, what are the topics you know good, and what are the topics you probably do not know at all. So I try to pick up the topic that will be interesting to as many of you as possible, but not too difficult. Okay, so as we don't have any problems to analyze, actually today we are going to participate, virtually of course, in Moscow Sub-Regional of New York 2015. Has any one of you seen the contest, or it will be new for everyone? Because I know it's available in Codeforces training, so you had an opportunity to see it, but that is pretty unlikely. Okay, so you have seen.
Which one?
2015, the last one. Nice. So no one. Okay. Also, I'll try like. It may happen that one day I'll give you the contest that you have already seen, but I hope this won't happen. If so, then probably I can give another contest to this team or think of something else. Actually, well, sometimes it's useful to participate again in the contest you have already seen. Sometimes you even do worse than you did the first time. Okay, one more question. We are going to use actually OpenTrains system that I'll give you login and passwords. Actually, it has a lot of contests, like I'd say several hundreds, and you will be able to access any of them. So feel free to choose them and participate after the camps ends. But who has been here last year? Okay, so you already have login and passwords, yes? You can use the same, but anyway, at the beginning, before we start the contest, I would like each team to contact me directly so I can like give you your login and password and set the right name of your team. So please come to me with the paper where you have your name of the name of your team. Usually, the name of your team is like some funny word, then the name of your university, and then please the names of all 3 participants. I think only surnames will be enough. So like when I look at the table, I do not see Unicamp team 25. Well, I see the people who are in this team. I don't think this will take us a lot, so if you start to come to me at like 12:30, we will be able to start the contest at 1. Okay, do you have any questions regarding this, like regarding participation? Also, if you during the contest you have any questions you want to ask, for example, you think that something is wrong with the judging probe. Yeah.
We're allowed to have 3 people on each team. 3 people on each team.
Yes. Well, yes, of course.
We have like 4 now. Oh, like 3 is the max. Just like the
well, actually, of course, there is no technical limitation for this. You will still be able to log in if you have 4 people. But if you have 4 people, I would recommend you to split in 2 teams by 2 people. Actually, you can mix every day. Like, if the goal is to find the best 3 or whatever. Okay, so if you during the contest you think that something is wrong, the checker is working wrong, or the test is incorrect, or you just misunderstand something in the problem statement, or you need an extra explanation to the samples, well, I can't guarantee that I'll answer the additional explanation, because usually if, like, an official competition, if you ask anything about the statement, you get no comments reply. The difference is only if there is a real disambiguation. So, but if you have any questions, ask them directly through the contest environment. There will be a special tab called Submit Question or Submit Clarification, like this. Use it. I'll be here during all the contest. I'll watch your questions and reply them as soon as I can. Okay, let's start with today's topic. So, as you have already okay, and I also need something to wipe off. Today's topic is Cartesian trees. Who of you, just answer by raising your hands, who of you have ever implemented any, I mean, not using the standard one, but implemented themselves, any balanced binary search trees? Okay, almost everyone. Like, what sort of balanced trees you usually use? Like trees or maybe splay trees? Which one? Black, red, black? Well, I think it will. Okay. Also, okay, then next option will be, after Cartesian trees, will be implicit key Cartesian tree that is usually named rope. And it allows you to treat the tree like it's an array. Have you ever implemented these things? Like, it allows you to cut away the segment, move it to front or to end, like this. And also persistent Cartesian trees. This is probably the most powerful thing, one of the most powerful data structure I have ever seen, because it actually allows you to do everything. For example, it allows you to create an array of size 10 power 10, like no problems. You can create an array of this size. Okay, let's start from the beginning and see how many things we can talk about today. So first, okay, you have the list of all main definitions. So just check the note if you have some questions, or if there is no answer here, raise your hand and ask me a question. So first of all, what is binary search tree? Binary search tree is some rooted tree, and every node has some key associated with this node. The main property of binary search trees is that the maximum of course, each node has only left and right children, or probably only one of them, or probably none. And the main property is that for each node, all the values that are stored in its left subtree are less than the values stored in the node. And same for the right. All the values in the right subtree, they are strictly greater than the one in the node. Okay, I won't write it down as it's already in your papers. So this is the main property, and also there is a useful statement that we will use to prove some things. Let's say that for every node, we will have two values associated with this node. It will be the smallest value in the subtree, like I'll denote this, or I already used another definition for the subtree. No? Okay. So let's mean value be the smallest value stored in the subtree of the node V, and max value be the largest, be the biggest value stored in this subtree. Then what we want to prove is, let's take any node V and any node U. We can say that the node U lies inside the subtree of node V if and only if the value, the key of U, lies inside this segment. Let me write it down. So U is inside the subtree if and only if it lies inside the corresponding segment. Oh, sorry, key. So we need to prove this, and then I'm going to use this statement to prove some other stuff. First of all, we can easily note that if we take the root, then this definition will be, this statement will be true for any node. If I take the root as V, then the definition, of course, will be true, because any node lies inside the subtree of the root. Okay, so give me a second. Oh, I used actually, XL and XR. There were another names for this. So, take a look at the root, and I'll see if. Okay. First, let's prove that if the value, we need to prove it in both directions. So first, if it's inside the segment, then it's inside the subtree. Well, actually, so let's take the node U and go from sorry for this pause, I'm a bit nervous. First time such an audience and I'm speaking in English. That makes me feel a bit uncomfortable. I'll do better next time. Okay, so again, if U is lies inside the subtree of V, then of course this is satisfied, because mean value, like, of course, if we have a set and we choose the minimum number, it will be less or equal than any number in this set. Same for the maximum. So the interesting part here is why is U outside the segment? If it's not in the subtree. Okay, imagine for a while that U is in subtree, but what we have proven now, that if U is in subtree, then condition is satisfied. Now I want to prove back, if condition is satisfied, then U is inside the subtree. Imagine that it's not. Well, sorry, strange. Okay, so at first I need to wake up fully. So again, imagine that it's not so. The value is in this segment, but we assume that U is not in the subtree of V. Actually, what we can say that if one node is lies in the subtree of another one, then the corresponding segment also lies inside the segment of this node. What we really want to see that these segments they have the same tree structure. Like if one is but any two segments. Sorry.
Now that you will access the tree of V, but you are assuming for the position that it is integrable, right?
Yes.
There are two cases. I think it's easier to break into two cases. One which U is the V is the tree of U, and then you got a computation, and on the other case that none of them is an ancestor of the other. If you break into two cases, it gets easier because you can see that either the intervals are directly disconnected or
yeah, you're right, I think. So what we can do is let's take the let's take the root and start to move from the root to node U and see how this segment changed. So again, I'm really sorry for this. I don't know what's the problem. We want to prove that if the value of key of U lies inside this segment, then U lies in the subtree of V. Let's say it doesn't. So here is the node V, and here it's segment, and U is having some like yeah.
Maybe you should. I would try something like I would look for U and 3 and V and take the last common ancestor from U and V. Would it help?
Yeah, probably. Let's try it. So we want to take the lowest common ancestor and
Maybe you can take a contribution.
well, if well, okay, that's really weird.
if it is this case, then it's clearly that they can't have the same interval. U can be negative.
Yes, of course.
The value of U is greater than the value of the lowest common ancestor, which is greater than the maximum value
Yes.
inside U.
Yeah, I got this. Yeah, thank you for moving me out of this block. Again, now I think I'm ready. The condition is satisfied, but we want to prove that. But we assume that U is not in the subtree of V. That there are two cases possible. First is U is V lies in the subtree of U. This is case number one. This case is obviously impossible because, of course, that will mean that the segment of V is included in the segment of U, just by the definition. Another case is both V is not in the subtree of U and U is not in the subtree of V. That means that their lowest common ancestor is different. So everyone knows what is lowest common ancestor. Okay, so just in case you forget it, it's the lowest node that lies both on the path from V to root and from U to root. Oh, okay. Let's take a look at the LCA of V and U. Then we can see that just by the definition of the binary search tree, all the values that lie in the left subtree are lower than the key value of the key of LCA, and all the values in the right subtree, they are greater than the value of LCA, than the value of the key of LCA. That means that all the values here are greater than all the values here. Of course, there is a symmetric case where U is in the left subtree and V is in the right subtree. But of course, from this we conclude that it's impossible for key of U to lie inside the segment. Okay, so now we are done with the statement. And what we need to do next is we need to define what is actually the Cartesian tree and why is it called Cartesian tree. So the idea is, there are different ideas how to balance binary search trees. So for example, in Adelson-Velsky and Landes trees, AVL trees, I don't know if you heard about them. We just use the rotations to balance the trees. So we, after adding some new node, there are four types of rotations. It's left small, left big, right big. And the idea is to rotate in such a way that we can say that always the difference of height of the left and right subtree differ by no more than 1. Then it's easy to prove that the size of the tree grows at least as Fibonacci numbers, and thus the tree is balanced. So what is balanced tree? Of course, all the operations we do with the trees that what are the usual usage of binary search trees? Just like the top of the rock. What is the easiest functions? These are implementing set. And this, to do so, we want to have add operation, find operation, and delete operation. Well, of course, this doesn't differ from what we can implement using hash tables. So, and the hash tables, of course, they have better work time than balanced trees. Well, they have randomized work time, but for almost all cases, we are okay with random times. But let's say we also want to do a lower bound, and now we are not able to solve this problem using hash tables, so we need binary search trees. Lower bound is, I think all you should know, just in case you forget, it's the smallest element that is greater or equal than k. Of course, in binary search trees, in this definition, we do not allow storing multiple elements with the same key. Well, this can be actually really easy fixed, but so far we will not consider them. Just think that all the keys are different. Of course, all these operations their work time, it's the function of the height of the tree. So actually, all of them, and it's is traversing from the root to some node. So the work time is the depth of this node. And that's why we want to balance the tree. So its depth is like O big of logarithm of the size of the tree. Of course, it's if it is about Fibonacci numbers, then of course they grow exponentially, so the time is logarithmic. Okay, now Cartesian tree is another approach. Oh, well, yeah, also I mentioned splay trees that are self-balanced trees. Well, they don't give you logarithm time for one operation, but they give you an amortized time. And Cartesian tree is just another way to balance the tree. What we do is, for every node, we have key, but now we have, let me denote key as x. And now we also add the new value called y. Okay, we will choose y's as random values uniformly distributed on some segment, but what we really want them to satisfy, we want y to form like a random permutation. But actually, if we choose it's just as a uniformly distributed number in quite a big range, then it's still okay. So in all the proofs that will follow, I'll assume that y are just like a random permutation. Okay. First of all, before we move to Cartesian trees, I want to take a look at the problem of choosing an increasing sequence greedily. So all of you probably know I'll use this part. Probably know the dynamic programming approach to calculate the longest increasing subsequence. Yes. But let's study the following problem, that instead of doing dynamic programming, I'll choose the longest increasing subsequence greedily. So we have some sequence, and what we do is we say that, okay, I take the first element as a beginning. Now I consider all elements one by one, and if the if element is greater than the last I took in my subsequence, I also include it in the subsequence. And so on. What we are interested in is what is the expected length of what's the expected length of the subsequence we will get. Who knows the answer? Yeah, it's logarithm, and it's actually pretty closely related to the Cartesian trees, but let's prove this. Of course, I forgot to mention that A is a random permutation. If it's not, then I can't say that this is a logarithm. Okay, so A is a random permutation, and let's t from n be the expected length of the length of increasing subsequence found by the greedy algorithm. What we want to prove is that it's O big of log. That is that I can choose some predetermined constant, let's say c, such that for any value of n, that condition will be satisfied, just by the definition of O big. Okay, what we will do, we will assume that this is, of course it's true for 1, because for this random permutation of size 1, the length of this subsequence I will get is always 1, because I always take the first element. Now assume that this is true for all n, and I want to prove it for all values from 1 to n. I want to prove it for n plus 1. Or let's say it's true for all the values from 1 to n minus 1. I want to prove for n. So let's study the process from the end to beginning. Assuming that this is a random permutation, so there are no equal values, for which element we can say for sure that it will be in the longest sequence? The greatest one, yes. So if we think that the ith element is equal to the maximum among all a, then we can say for sure that this element is included. Moreover, we can say that all the elements that follow, they are not included. No, by the definition of the greedy algorithm. And actually, okay, so we can just throw away this suffix and throw away a, and take a look at what's going on this on the sequence that is the prefix of a. Of course, as a subsequence of a random sequence, it can be of random permutation. It can be treated as a random permutation also. So what I can write is that. Okay, and what's the expected position of the maximum? It's somewhere in the middle. So before we do the proof, just the common sense, if it's just around the middle, that every time I take the maximum value, I throw away like the half of the sequence. So this should be like logarithm time, like the same as in finding medium value in linear time or quick sort. Okay, so the length of so again, t is the expected length. It's 1 for the biggest element plus, of course, all the probabilities that the maximum will be located at any position, they are equal, just because this is a random permutation. So the following is true, yes. Okay, so any no questions, yes? Now, why is this logarithm? We can actually put the definition from here, yes, and place it here. So it will be less or equal than Now, as I want to estimate from the top, from the upper bound, I need to round this up in some way. I'll split this in two, like, let's say, values of e that are greater than the n divided by 2 and that are lesser. And now I can round this up to the log n, and I can round this up to log of n divided by 2. And oops, yep. My lecturer in calculus always hated the people who forget about the c. Now we can replace this with log n minus 1. C. Okay, the last thing we need to do is open the brackets and say that this is equal to 1 plus plus what's going on here? I open the brackets, it's n half of n multiplied 1 with n, c. That's yeah. And of course plus this. Oh, sorry, I already merged them here. Okay, so the only thing we need to do now is we choose c greater, sorry, of course minus, or this won't work. The only thing I need to do is I choose c greater or equal than 2, and the provement is okay. So we finished. I don't know. This is just the regular way you solve like recurrences. So any questions? No. Okay. Well, this is. I can't say that this is just like directly related to Cartesian trees, and the proof for Cartesian trees will be the same. But this really helps. At least for me, it really helped me to understand why Cartesian trees work in log time. Okay, and now finally we can move to them. So as I said, for every node, we have key and also some additional value associated with this node. And these values, we treat them as a random permutation. We want to build a tree such that from the one hand, it's a binary search tree according to x, but from the other hand, it's heap for y. So the heap condition is satisfied for each node. That is, let's say it's heap on maximum. Just because I want to paint the Cartesian trees as they are to paint, because like Cartesian plane, we'll build the heap on maximum. So for every node, I say that it's less than, for every y, I say that y in the node is lesser than the y in the parent. Next statement is, okay, what we are interested now in, how many ways are there to build the Cartesian tree. So both heap condition is satisfied and binary search condition is satisfied. The answer is 1. So we want to prove that for any given set of pairs x is and y is, if all x are distinct and all y are distinct, there is exactly one way to build Cartesian tree. Well, this also can be easily done by inductively moving. Probably I should see how to spell this word. How do you call math induction? Induction. Induction. Okay, thank you. So of course, if the size of the set of pairs is 1, the answer is unique. There is only one tree. The node, the x1, y1 serves as a root. Let's think that for all the values from 1 to n minus 1, the answer is unique. Let's prove that for some n, it's also unique. Because we have heap condition, we can uniquely determine which node will serve as the root of the tree. Of course, this will be the one with the maximum value y. Well, because if it's not, then take a look at this node. For it, heap condition is broken. So the root has maximum value among all y. But now we also have a binary search tree condition, and it says that in the left subtree of y, there are all the nodes that have x smaller than x of root. And in the right semiplane, we have all values that are x are greater than x of root. So what we do now is we divide. Yeah, as you already mentioned, I now treat them as points on the plane. And that's why, of course, it's called Cartesian tree. So I move all the points with x less here and all the points with y here to the right plane. But we also know that for the smaller sets, the tree is unique. So here, for this set, the tree is unique, and for this set, the tree is unique. And now the only thing I have to decide is which node can be the left child of root and which node can be the right child of root. Of course, there are not more things I can choose here. I have to make the node with the greatest value the root. So the greatest value in the left semiplane becomes the left child, the greatest value of y. It becomes the left child of root, and the greatest value of y here becomes the right child of the root. Okay, so the answer is unique. What we want to do now? Now we want to prove that I'm not going to prove that the depth of the tree is log, because that actually may require a lot of work. But we do not need this. What we need to prove is if I take any node, that the actual depth of this node is log n. So feel the difference. I'm not going to prove that maximum among all depths is a log. Why? Well, because expectation, it has linearity and so on, very good stuff, but the working with expectation of maximum is really terrible if you have ever tried. Moreover, we do not need to prove the depth. We only need to prove the expectation for any node. Okay, so but before I move to proving something, I need to explain how does this tree work, because so we know what to prove. Like, we have already proven that this tree is unique, but how do we build it? How do we work with it? The main idea is to have two basic operations, and all the things done with the tree are performed using these operations. These operations are split, it takes some value k and returns two pointers to the roots of two subtrees, of two trees, actually. Split and merge. Well, as you can guess from their names, split splits one tree in two, and merge merges two trees in one. So split, it also receives a tree actually. So split operation, it gets the pointer to the root of some tree, and it reorganizes the tree in such a way that there are now actually two trees, one having all the values that are less or equal than k, and another one having all the values that are greater than k. How does it work? It takes a look at the root and sees which excuse me, before I move to the description of the operation, let's just use a common sense. Of course, the result of the operation is unique, because we can again treat the tree as a set of pairs and divide. How we can perform split in linear time? We can just treat these operations, treat nodes as pairs, separate them by their value of x on the lesser or equal key and greater than k, and then we have two sets. We can build Cartesian tree using them. Oh, I actually haven't told you about how do we build Cartesian tree in linear time. Well, of course, we can only do this if it's already sorted by values of x. Who knows how to prove that it's impossible to build a Cartesian tree? Actually, not Cartesian, any balanced tree, that it's impossible to build it in linear time. Well, it's actually just the idea. Oh, no, sorry, my question, yeah, you're right. But the question was how to prove that it's not possible to build it in linear time if pairs are not given sorted by X. Yes, absolutely right. Of course, we can always get, if we already have a tree, we can get sorted array of its keys just by doing a left-right traversal of the tree. But if we can build the tree in linear time, that means we can sort the data in linear time. But as you, I think, know, it's impossible in standard computational model if we assume we can use only direct comparisons between elements. Okay, but anyway, let's get back to our Maton. If we can separate the set of pairs and then build the trees here. So we know that the result is unique. We know how it looks like, but now we want to achieve it faster. We take a look at the root. Of course, the root will still be the root of one of two trees, because if it has maximum value among all y, it will have a maximum value among some subset of them. That means what I need to do is I need to check how the root opposite to k, let's say it will go to the right subtree. That means I already know the root of the right subtree. So yeah, I want to return two pointers. Pointer to the root of the left subtree and pointer to the root of the right subtree. Like, not subtree actually, now it will be left tree and right tree. So I know the root, so I can already say that R is the root. Root has its left subtree and right subtree. What can we say? We can say that the right subtree all lies to the right from the value k. Because, just because all the values in the right subtree are greater than the value in the root, the value of the key in the root. That means I do not need to change anything with my right child. But if I look at my left child, then probably some of its values should go to the right subtree, some nodes should go to the left subtree. What I do now is I call split from this node. This split returns me two subtrees, and the right of these subtrees, it becomes the left subtree of the root, and the left subtree becomes just the left tree in the answer. So I did some constant number of operations and reduced but the depth of the node in the original tree is increased by 1. So how to describe the total work time of this stuff? Actually, if we take the picture of what will be the result, I'll draw another picture, sorry. So for example, the initial tree looks as follows. Okay, so imagine this was an initial tree, and the split operation was called for this value, for this line. What are the edges I will use? Actually, these are all edges that cross this line. And what will be, how will the resulting trees look like? there will be no edges crossing this line anymore. So this node will become the left child of this. Okay, this will be the left, this will be the right as a result. So do you see the idea, yes? Any questions? Okay. Moreover, I can now easily describe the work time as the length of the left path of the right tree and the length of the right path of the left tree. So the left path is the path that you get if you stay in the root and traverse to the left as long as it's possible. So this is the left path of the right tree, this is the right path of the left tree. You can see that all these nodes, they were counted once, at least once. And I can say that the expected number of operations is equal to expected number of left path and expected number of right path. But what is actually the left path? If you order all these nodes by, like, just put them in an array with sorted values of x, you can say that it's absolutely similar to this problem of having a grid greedily taking a subsequence. Because yes, you always take the first, and then actually the parent of this node is the first node greater. This is not a formal proof, of course. This is just to give you an idea how is this problem related to Cartesian tree. And same for the right. Here, for the left tree, and I take a look at the right path. Okay, now I want to take a look at merge operation. What is merge operation? It takes two trees and merge them in one Cartesian tree, also in log time. Of course, the trees are should be non-intersecting by values. That doesn't mean that they should not contain the same elements. That means that the maximum value in left should be strictly less than the minimum value in R. If it's not true, if we can say that we can merge trees that intersect, we still can prove that we can sort in linear time, so this is impossible. Okay, so merge operation, it takes two trees, the property I just described. Actually, I do not need to paint something else. We can just merge back these two trees. Why not? How does it work? The whole idea is the same. Let's, in constant number of operations, recursively run from some node that lies deeper. First, we take a look at two roots. Which node will be the root of the resulting tree? Of course, it will be the node with the maximum value. But if you want to pick the maximum from the set, and you have split it in the two subsets, you can pick maximum in the one, in the first, pick maximum in the second, and pick the maximum of two. That means that the maximum value of y is either y of L or y of R. So what I need to do is to pick the one that has bigger value of y, and say that it's now the root of the tree. Here on my picture, I already have R greater than L. And now I just call it the root. What happens then? I already know the root, and that means, okay, again, let's think that R is becoming the root. You can paint absolutely the same picture for the case when L is bigger. If R is bigger, I do not need to change anything in its right subtree. But if I take a look of its left subtree, what I need to do is to take left subtree and the left tree of the query and call merge. And then just take the resulting tree and say that it's now the left child of root. Again, what is the number of operations I'll do? I'll perform. It equals to the sum of the right path of the left tree and the left path of the right tree. Because I'm only considering nodes that lie on this path, and every time I move down the path in left, or in right or in left tree. Any questions so far? Please feel free to ask. Well, you also have this paper, so I think there are many answers here. And then, okay, now we know how to do split, how to do merge, but how do these operations help us to establish a binary search tree? Well, actually, it's easy to see how to do all the operations using this split and merge. First operation is to add an element. To add an element that has some value, like let's say that it has some value a, I need to take the current tree and split it into, well, let's assume that I'm adding a new element and I know that there is no element with this value in the tree. I need to split it by a. That means I get two trees. Now I create the new node that will correspond to this element. And now we need to get back to one tree just by calling two merge operations. First merge left tree and the new node I just created, and then merge the result with the right tree. Well, order can be different, but the idea remains the same. I won't paint delete and find. I think you already got the ideas. Question? No. You already got the idea, so you know how to delete an element and find. So to delete, I call two splits, take an element, just remove it. I don't know. It depends on the implementation. Maybe I call delete or do something else. Just free the memory and merge two trees to one again. And to find also the same, I do two splits and see if I got the node or one of that or this tree is just empty. Also, how do you do lower bounds? Well, I think you got the idea. You just do cut and then take the leftmost element in the right tree. Well, my personal impression for using Cartesian trees is that they are very slow. Like, they are slower than any other balanced tree you can imagine. Like, it's 10 times slower than red-black, for example. And if you take the implementation of red-black from standard library, then just do not try to compare. But what's the good point of these trees is that implementation in standard library, for example, it has operation lower bound, but it can't answer queries like what is the kth element in the tree. So like nth element, you can answer it. You can't answer it using set. Why I tell you about this tree, why I like them, is first of all, they have very easy implementation. Maybe I was talking for a while and got too specific sometimes, but what you really need to implement is split and merge, and all other operations are just combinations of 2, 3 splits and merge. And split is actually about, I don't know, 7 or 8 lines of code, same as the merge. Like this. You see one case, you see if, so in merge which one is bigger, and in split which one does the root go to left or to right. And so easy implementation is really important for programming contests, because even if you have your team notebook during the world final, if the code of the tree is long, you will spend a lot of time just typing it from the node. And also, of course, the main advantage is that we can upgrade Cartesian trees to do, well, actually to do almost everything we want. I'll talk about it later. I think now I should finish to prove. Yeah, and we go to the proof of the depth of random node. Sorry, not random node, just expected proof of some node. Oh, expected proof, expected depth. Okay, we need another statement to prove the depth. It's let's make the left-right traversal of the tree of the nodes. So, as I already mentioned, left-right traversal. Left-right traversal, if you don't know, it's like just depth first search that first goes to the left subtree, then prints the value of the node, then goes to its right subtree. So here are the y. It's sorted by x, and we are just we are interested in y's. The statement is, it's actually in your, I think it's in the papers. If we consider two nodes, again v and u, node u is among the ancestors of the node v if and only if it's greater than all values of y on the segment from v to u in left-right traversal. So we want like okay, no questions regarding the statement, yes? Let's prove it. First, we want to prove that it's not the biggest value on this segment. So, for example, there is some, like, let's say this is yv, this isyu, and here is yif. If there is some yif that is greater, well, yeah, of course, if yv is greater than yu, then nothing to talk about it. You can't be one among the ancestors. Yeah, I'll consider the node to be among the ancestors of itself, but that actually, just to satisfy the statement. If there is some node E between them such that it's greater. Okay, let's take a look at the greatest, at the node with the biggest value of y on this segment. What we want to prove is that this node is actually the LCA of V and U. Okay, let's say it's not, and we can take a look at well, first yes, let's take a look at the LCA. Case number one is that okay, it's located. Yeah, we know that actually V and U are located to the different sides from that line. But still, we suggest that LCA is different from E. So let's see the path from V to LCA and from U to LCA. What we can say about what we can definitely say about the LCA and the location of V and U regarding to LCA. Of course, they are located in different subtrees. Like V should be the left child of ACA and U should be the right in the subtree of the right child. Why? Well, because if they are both in the same subtree, then this is not the LCA. We can go one step deeper. Okay, so that means that U lies in the right subtree and V lies in the left subtree, and the key of U is greater than key of LCA, the key of V is smaller than key of LCA. But what does that mean? Of course it means that because in the left-right traversal they are sorted by X, that means that LCA should lie somewhere on this segment. Yes? But then, what we assumed is that we now know that LCA lies on this segment from the one hand, but from the other hand, it's not the maximum value on this segment. So there is some node E. Okay, I'll denote LCA as W. There is some node E that actually, because it's maximum, it should be higher than the node W. If it's higher, it means that W should be in its subtree, yes? But just take a look. What we know is that all the values here are like greater, and all here are smaller. But if these two nodes, they both are in the subtree of omega, that means that E lies on the segment of W. Do you remember the statement at the beginning that one node lies in the subtree of node U lies in the subtree of the node V if and only if it lies in the corresponding segment, its value. What we have now here, that E lies on the segment of the node W. Why? Because we know that both V and U lie in W, and E lies between them. But that means E should be in the subtree of W from the one hand. But from the other hand, we know that the value of Y of E is greater than the value of Y of W. So from the one hand, binary search tree condition is broken. From the other hand, heap condition is broken. That means that such situation is impossible, and the biggest value on this segment is actually the LCA of these two nodes. And from this we conclude that if we want U to be the ancestor of the node V, the only possible way is that it's the biggest value on this segment. Okay, we are almost done now. Now just some simple usage of expectation. We can say that depth of the node V is equal to the sum among all nodes U is ancestor UV. The depth of the node is equal to the number of its ancestors. Pretty obvious. Just equal to the length of the path from root to this node. Let's treat this as an... actually, this is an event. We can treat this as an event because we have a random permutation, yes? Moreover, the linearity of expectation, it doesn't care about the independency of the events. So I can say that... no, I can't say that. I can say that the expected depth of V is equal to the sum among all V expected is ancestor, where this is actually just considered to be 1 if event occurred and 0 if it didn't. That is actually equal to the sum of probabilities of what? What is the probability of an event that the specific element is the biggest on the segment of length, let's say k, if we assume y to be a random permutation? It's 1 divided by k. Yes? And also I do not care about, I do not need these events to be independent. So what I can write here is that it's less or equal than 2 multiplied by sum from 1 to n. This is all bounded up because I can move from the node both to left and to right. So this is why I put 2 here and round this up to m instead of writing actual limitations. Any questions so far? Yeah.
In the summation, you put age and containing b. In the summation.
In the summation,
Yeah.
h, where I don't have h. You mean u? U in oh, this is like all nodes. Sorry. Yeah. That's a bad definition. I just always use V, like, as to denote the set of nodes of the graph, but it's bad here. You're right. I write subtree of root. But this is the well-known sequence from the course of calculus. I think everyone knows that this is bounded by log n. So now we are done with the proof. Well, if you do not like me to write, that's not okay to write in this way. This is true for definite, true for sure. Now it's strict. I think we should have a small break now, and then I'll turn about implicit key Cartesian trees and what are the usually the operations that allow you to do. This is actually why you need Cartesian trees, because to solve the lower bound problem you can use any binary search trees. Let's have like, I think 5 minutes will be enough.
Could you explain this stuff here?
Yes, sure. So, okay, you got this step, yes? That the expected depth is expected number of ancestors. And also we prove that node U is ancestor of node V if its maximum value on this segment. But that means that the expected number of ancestors, yes, I can insert actually one more intermediate step. I can write here that it's the sum of probabilities that this node is ancestor, this node is ancestor, this node is ancestor, and so on.
Everyone who doesn't have a badge or wasn't with the name in the list, please come here. Is there anyone who doesn't have a badge or doesn't have the name on the list? Your name? Everybody?
Yeah, so,
I know there is
but
Paulo and
this is the sum of what is the probability that this node is an ancestor of this node. It's that this is the maximum of this segment, plus the probability that this is the maximum of this segment, and so on. And this I write for all the segments. And now I just want to estimate it from the upper bound. I put 2 here because I go in 2 directions, and I put n here because the longest length of the segment is n, where n is the number of nodes. And because I can do this because they are in these events they are not independent, but I need only expected value. So because of linearity, I cannot care about independence. So have I answered your question?
Yes.
Okay, sure.
The match operation. The two trees. The max element on the left tree must be smaller than the smallest element on the right tree, right?
Yes, if I want to perform merge, I need the maximum in the left tree to be smaller than the maximum in the right tree. If it's not so, I can just merge them easily.
You have proved that the pairs make the tree be unique, but have you proved that it already exists? That you can indeed build it?
That you mean like that there is at least one such tree? Well, it comes from the proof, but the proof is giving the algorithm of how to build this tree is given in the proof. You pick the maximum and call it root. Now split in 2 parts, and build trees there, then merge them. But also there is an algorithm of how to build a Cartesian tree in linear time. I think I'll have some. It's easy traversal to the stack. I think I'll tell it.
The question he asked. You can build a balanced tree this way. You always can build a balanced.
If x are sorted. If I have the pairs sorted by x value.
Yeah, and you still have the heap condition in the y.
Yes, because I always pick the maximum value and call it the root.
Oh, okay. So you distribute the y.
No, I arrange my pairs by x. Yes, so it's x1 y1, x2 y2, and so on. And I know that x form an increasing sequence. Now I pick the biggest value of y in all this sequence. Like let's say this is this. I call it the root. Heap condition will work for it because it's the root of the tree.
But you
It's the biggest value, and it's the root, so the condition works.
okay, the heap condition, but
Yes.
the balance in the y, in the x.
Yeah, you have it already.
And now I split them in two parts by x. All pairs that have x smaller than xk will go to the left subtree, and all pairs that have x greater will go to the right subtree.
In the case I have the permutation y is a permutation of 1 to n, and I have 1 to n.
It's random. It's not 1, 2. It's random permutation.
Yo, I'm taking a
Oh,
specific case.
yes, but what is the probability of this case?
Yeah, and this is what I'm asking.
Yeah, this.
If I have this case, 1 to n, I can build a balanced tree.
Yes, it will have a height of n, but what we're estimating is the expected depth.
Yeah, they expect.
That's like, when you run quick sort algorithm, it also can work in square time. Okay, I need. Do you know where is the water closet?
Yes, again, the people of this
Okay, thank you. Excuse me, where can I wash hands? Where's the restroom?
By the way, that's too glad.
Nice to meet you, but my hand is.
There is one here downstairs and another there.
Thank you. And this one doesn't work or works bad?
It works, but it's for the live stream.
Okay.
These men
This doesn't work. Thanks. Oh, thank you for your help at the beginning. I was like still asleep and trying to remember that this is very easy. What's wrong?
Do you call Y E Greek? I have never heard that before.
And how do you call it?
Y.
Why?
Yeah.
Oh, yeah.
Yeah.
Sorry.
I have never heard it.
I'll try to say why.
But in Spanish is E Greek. It's the same.
Because in Russian it's also Y and probably it's Y. Yeah.
Very nice.
Okay, but so you understood that we made.
Just remember the third time is okay. I understood that.
We're not used to that. I have never heard actually in English.
That's because I have poor experience of giving lectures in English because I usually do them in Russian, of course. That's why. Okay, thank you.
It's first time you.
No, it's not the first, but third time. And probably the two previous ones they didn't contain. That's why.
Yeah, but the lecture is nice.
It's really nice.
Yeah, you like? Oh, thanks. But do I speak?
Lugar que ele possa ir com água quente.
Are you sure I need the room one? Is it? I speak quiet, or people can't hear me?
There's been one guy complaining, but it's just one guy. If you don't want to use it,
Well, let's try it first. 1, 2. I just want to because then you speak and then you hear yourself, but with a small delay, it's almost impossible to speak.
yeah.
Can you turn it on so I'll try it?
It's already on. It's already on. Let's give a test.
1, 2.
Because people are speaking, but if you.
Okay.
It's the same time.
I don't hear myself.
I think you're speaking very loud. This one guy is complaining.
Just one guy complaining. But if you don't use it, you want to use it.
Maybe
there's no problem.
that was because sometimes I speak to myself or something. He wants to hear this also. Okay, I'll. Yes. You did it already. Okay, so. Okay, I think maybe I can pick it out. How many problems can you solve? Well, you can, and you have you upsolved them. So you do like if you complete the second time. Okay, I definitely agree with that. And have you read from all permutations of size 10. Yeah. Then you can be pretty sure that it's correct. So I just know the story about the team. They came to the world final, and there was a problem that was pretty straightforward usage of Hungarian algorithm. Well, min cost max flow or Hungarian. And they had this min cost max flow in their team notebook, but it contained an error because the tests were too weak on the you can imagine what happened next. The world final was completely spoiled because, well, if you're trying to find an error in your code, mistake in your code, the last place to look for is the code the last place to think of is your team notebook. So be sure that it's better to not have a code in the team notebook at all than to have it not tested. And now back here. So I was talking about storing additional values in the node of the tree. For example, I can calculate the size of the tree in this way. When should I call this recalculation? Every time you do split and merge. Every time you do split and merge, just at the end. So take a look here. This is the result of the split. What nodes really need this value to be recalculated? Only the nodes along the right path here and left path here. So these are exactly the same nodes that you were able to these are exactly the same nodes you called split function from, that were used by split. So just every time you finish at the beginning of split or merge, call recalc function, and it put all these values you need to recalculate in this function. Well, you are probably interested in where can you see the code of this tree. I don't know good English sources. Well, you can go to Codeforces and pick any problem that requires this tree, and then go to like some cool guy code like tourist or so, and just see that there is a site. It's in Russian though, but the code is not in Russian, of course. So I don't see any problem. The only thing you need to know is you need to find where is the Cartesian tree article here. I can help you with this, or you can use Google Translate for the whole page. So the site is, as long as I remember, this is the name. It contains a lot of code for standard algorithms. You can ask me. I'll give you the direct link to the code of the Cartesian trees. But please first try to implement it yourself before looking how it should look like. It's always better to try to do it yourself, because if you just copy the right code, first of all, you will never remember it if you just copy it. And second, you do not know what are the possible mistakes if you copy it. And if you you took all the mistakes by yourself, you will remember them surely. Okay, so this is how we maintain the size of the tree in the node. How do I now answer cuff element query? As we know that nodes are arranged by the x value if we do left-right traversal. So let's do the sort of left-right traversal. I stay at the root, and now I decide, do I need to go left or do I need to go right, or root is the answer. What I need to do is I need to check the size of the left subtree. If size of the left subtree plus 1 is equal to k, then root is the node I'm looking for. If it's less, then I should subtract this value from k and go right. If it's greater, I should go left. So just traversing from root to the leaf until I find the right node. So every time I go to the right, it's similar to skipping all these nodes in the left-right traversal. Because if I go to the right, I go to the node that is for sure, I can be sure that all the nodes in this subtree, they are greater than value here. So I just skip them. Actually, this is one of the reasons why this tree is called binary search tree, because it's pretty close to doing binary search. But instead of doing binary search, you traverse down the tree. Okay, so this is how to solve the cuff element problem. First usage of Cartesian tree that we cannot just replace with using a standard template library. Any questions here about this problem? No. And now, what is implicit key? Oops, sorry. What's the whole idea of implicit key? It's pretty fun. It says, let's just forget that we have x. We do not need them. Just why do you need x? Where is it used? It's used in split operation, yes? In merge, no x is required. Let's replace x with just the position of the element. So now the value of the node is equal to its position in left-right traversal. And no x is required. How do I do merge? Nothing changed. Exactly the same way I used to do it before. How do I perform split? In split, instead of using value x, I use the size of the tree. So, and now split looks like so before split was take the tree root and split it on two subtrees, on two trees, with one having all values less or equal than k. And now it's take the tree root and split it on two trees, one of size k and another one of size n minus k. So just take first k nodes and put them to another tree. As you can see, the split will work exactly in the same manner as split before. But why do they need this stuff? What we can do now is we can operate with segments of. So we can treat the structure as I remember is called rope. But I need to check. Maybe rope is already a persistent structure that is even more powerful than just implicit key. But let's get back here. What I can do now is I can treat this tree as an array. But an array where I can do operations. I can access every element in log time. I can change element in log time. I can remove element from the middle of array in log time. You know, like when I only started to program, it was like the structure of my dream. I was always wondering, why can't I just insert the element in the array in the middle and shift everything? It took too long, and now here's an array of your dream. It allows you to insert element at the middle. For example, how do I insert element? I split the tree. Now I create a new node and merge them in the same order. Okay, I can add elements, remove elements, but that's not all. One more thing I can do is I can shift the whole segment. For example, why should I care that I merge them in the same order? There are no keys now. In the original merge, we had the statement, we had a condition that when I'm doing merge, I need the maximum value in the left tree be strictly lesser than the minimum value in the right tree. And now, nothing prohibits me to swap them and merge here the tree of size n minus k, and here I take the tree of size k. That will be equal to taking some prefix of an array and moving it to the end of this array. Why not? Still everything works. I still can access any element. And actually, you can still check all the proof regarding the height. They will remain the same. This is powerful. Yes, for example, it allows us to replace segment trees. I wouldn't recommend replacing segment trees by Cartesian trees if you can still use segment trees. Who knows segment trees? Almost everyone. Nice. Because Cartesian trees are too slow, as I mentioned at the beginning. Like, if you compare them to segment trees, they will be like 20, 30 times slower. But still, all the asymptotics, they all remain the same. You can, for example, why not? In the node, I can store the sum of all elements. Like, as I said, I can use this as an array. So why not store the sum of all elements in the subtree in the node? So how do I now answer the query of sum on the segment? I take the tree, cut the segment I want from it, and take the sum value in the root. That's all. Same as with maximum, minimum. This is powerful, yes, but this can be even more powerful. For example, we can also revert segments. Assume you have the following problem. You're like given a string, some string, let's say S, and you want to be able to do the following operations. First, you want to be able to insert a new letter in the middle of the string, at any given position of the string. Like I take the string S and just insert some new character here. I want to be able to delete the character. And I also want to be able to compare two strings. Just take two substrings of this string and check if they are equal. Do you know polynomial hashes? I think you should. Like hash functions on strings. Who has at least once implemented polynomial hashing? Not many. Okay, but for those of you who did, so if I store my string in the Cartesian tree, then I have some letter associated with the node, some string in the left subtree, some string in the right. So how do I compute? If I know the hash functions of all the subtrees, how do I compute the hash function of the whole tree? Just take hash of the left, multiply it by p in power, no, don't multiply it at all, plus hash of a single node or single letter multiplied by p in power size of L, plus hash of the right string. It depends. Actually, when you implement polynomial hashing, there are two different approaches. You can increase powers of p from left to right or from right to left. But that doesn't change formulas much. Okay, that means I can, in log time, compute the hash function of any substring. I can just cut this substring away from Cartesian tree and see the value stored at the root. Then same, I put this substring back, take new substring, compute its hash function, and now just like when you compare strings, you can compare the hash functions instead of comparing them directly. So we can insert character, erase character, and compare two substrings in log time. But that's not everything. We can also flip substring in log time. That is, the query is take a substring and reverse it. Just replace it with flipped one. How? Actually, pretty easy. What you need to do is, in any node, Do you know who knows about lazy propagation of modifiers in segment trees? Well, for those who do not know, I think we are going to have another lecture contributed to segment trees, and I'll tell you about this. And also for the one who already knows, I'll tell some very powerful usages of segment trees. So for those who know the idea of lazy propagation, you can still do the same in Cartesian tree. You can store the modifier at the node and just push it anytime you visit this node. So when in the split or in merge, you come to this node, you push the modifier. That's all. One of the possible modifiers can be reverse. So the only thing you need to know is how to push reverse modifier. For example, I know that flag is true in this node. That means I need to consider not this string but reversed one. How to push the modifier? You just set it here to false, push it to your children, and then swap them. The way to reverse the string is actually like reverse left half, reverse right half, and swap them. So same you do here. You push reverse modifiers and swap left and right children. So now you can even flip strings and still compare them, and Cartesian tree rules the world in log time. That's probably all that I have to tell you about that I wanted to tell about implicit key Cartesian tree. So I'm not sure if I need to move on with persistent trees, or the amount of information I gave you is already too big. Or maybe we can just solve some problems now, or see how to apply these trees. Okay, now, well, I better tell you, I have half an hour. At least I can give you the idea of persistent data structure. Who knows about persistent data structures just in common? And which structures do you know how to make persistent?
Linked list and segment tree.
Again?
Segment tree and linked list.
Oh, if you know, linked lists. Yeah, if you know how to make persistent segment tree, this can be pretty easy to you. But as there were only two people, I think I should give some additional clarifications on what is. Well, the fun fact is that persistent implicit key Cartesian tree, it's not Cartesian and it's not tree. Because the first thing you do to move to implicit key, you forget about y. So now there are no x, no y, but it's still somehow Cartesian tree. The whole idea of persistent data structures is we want to be able to access any version of a data structure. Like, we have a list of queries we perform. Example, first query, second query, and so on. And at any moment of time, we are given some Cartesian tree, and we are able to do any operations with it. But we want to have the following option. Imagine I performed 10 operations, and I want to do the following. Okay, and now I want to take the tree that I had at the step 3, after the step 3, and add value to this tree. and then probably I want to merge them. This can actually be done to any structures, because you can always, instead of making changes, like you can take the code. At some moments of time, the code goes to memory and changes the value that are stored in the memory. Yeah. You can take any structure, and instead of changing, like if there is you assign a new value to some variable, you can, instead of changing this value, create the new variable. So the idea is everything remain constant. No, values never change. Well, this is a pretty hard stuff to get. Why would we need this? We need this because what does it mean applying to Cartesian trees? Sometimes in Cartesian trees you change the nodes. You change who is the left child, who is the right child. But now, instead of changing every time, you will just create the new node. You'll create a new node, and well, this is probably too complicated idea to show it on Cartesian trees. Let's do the following. Let's have a linked list first and see how this idea works on linked list. Okay, so I have list. I know previous and next element for each node. And imagine now that I perform the query that is insert new element at the beginning. So that is create some node, and not at the beginning, at the middle. Let me go to one directed list, because just to reduce the amount of job. Okay, so what I want to create now is this node in this list, and after this insertion, I want to be able to access both lists, the previous and the next one. Well, of course, I need to pay. I need to pay this complexity sometimes. But how will the new list look like? So as you can see, the only value that is and the new one appears. So instead of changing, okay, but for this node, I need to store not only I need to store 2 edges, and for every edge, I need to have a number of versions. So, like this was version 1, and this is the edge that has version 2. And now, if I want to access some specific version of list, I need to tell which version I want to use. Okay, this is probably because here I need to store some additional information, versions, and so on. We'll use even easier stuff to the persistent stack. So, sorry. Push, top, and pop. And to the end, get the top there. This is a sort of interface to take the, again, I have a sequence of and what I want to do I want after every iteration store the current head of the stack. Now I can access both the stack after operation 1 and the stack after operation 2. That depends on directed tree. And
Well, actually, I can say that this is a very powerful idea, and if you hear this for the first time, that it really may be hard to understand. But if instead of changing the values, I just create a new one, I can have the same structure, but I can access all the versions of this structure. Who got the idea? Okay. Now let's apply this idea to Cartesian trees. Things are not
Cartesian trees.
This will be left, and there will be no right child. Here I create a new node called 7 that has this node as its left, this as its right. Okay, so this is how the graph looks like after I did persistent split. And now I'm still able to access the initial tree. But from the other hand, I am able to access these trees. And no problems that they share the same nodes. Because the main idea is we are never going to delete anything. Well, actually, when you became an experienced user of persistent data structures, sometimes you need to do garbage collection or the memory consumption will grow too fast. Because you see, any operation requires to create log n new nodes. So this takes a lot of memory. And also it's much slower because of the memory consumption. So think of it. Now I can access Cartesian tree at any moment of time, do some operations, and still take old tree, new tree. What I can do is this is the easiest usage, just access old copies. But we can go deeper, and actually the operation we are able to do now is we can copy the segment of an array still in log time. So for example, for this tree, I can do the following operation. Take some substring and copy it here. Just do you understand what I mean by copying? Yeah? Just copy all the values from here to here. Replace the part of the string. How do I do this? Because in normal implicit key Cartesian tree, when we were merging two trees, to merge, I need two different trees. But now I can merge the tree itself. Why not? This is valid copy, this is valid copy. I can treat them as, I can treat one instance of a single tree can be treated as two different trees. So to do this, I can cut the tree in 5 segments. And now they are numbered segment 1, segment 2, segment 3, segment 4, and segment 5. I merge them in the order 1, 2, 3, 2, 5. And I get the string where this fragment is copied. Well, let's move on. Do you want an array of infinite size? Well, okay, let's say not infinite, but size 2 power 64. Why not take a single node and merge it with itself? You will have array of size 2. Merge it with itself, you have array of size 4, and so on. So after 64 operations, you will have array of size 2 power 64. And you can access any element. Why not? I think this should be mind-blowing, actually. I was mind-blown the first time I realized what can I do. So actually, this is not, there are no x's, no y's, and it's even not a tree anymore. It's some directed acyclic graph. Because this array will look like, I think we need, yeah. If we draw, what happens? Okay, I take 2 copies. Yeah, when I take 2 copies, one of them becomes, or that will be the array of size 2. Now I join it again to itself, and what I have is some sort of, okay, I create new node, and its left shell is this, and it's, I think it's, okay, yeah, I have, it's really hard even to draw. We call merge of these 2 trees, yes? How do we merge them? We took, for example, this as the new root. As I always create a new copy, I create it. This is my left sum, this is my right sum. But these are actually the same nodes, so yes, this is how the graph will look like. And you can continue this operation. So that's it. There is only one thing you need to know about persistent Cartesian trees, that actually we can no longer, I said that we do not have y. How do we merge trees then? And why can't we use y's to merge trees? It's easy to show that if you still continue to use y's, it's possible to create the test that you will always have a bamboo. So instead of comparing y's, we need some sort of random merging. What is random merging? When I want to, if I erase pictures too much, just feel free to say I'll try to use all the space before erasing something. So imagine you want to merge the trees. I'll paint them in any way, but as you already noticed, they may share the same nodes. Why not? At the beginning, we used to compare y's. And now, we want to have some comparison that is random and it doesn't depend on any value of y's, but it still has the same property. Like, the result is the same. What was the idea of merging? Who will be the root if I merge 2 trees using y's? The node that has the biggest value of y in it, yes? And if the size of this tree is A and the size of this tree is B, the actual probability for this tree to become a root is A divided by A plus B. So I want, but we used here that y's are independent. And now we cannot use that y's are independent because they may share the same vertex, the same nodes and so on. So I need some comparison that depends only from the sizes of the trees. So yes, what I do is I still maintain this additional value. I already raised it. The size of the tree. And now I merge them according to this size. So the left tree will become the root with probability size of left divided by size of left by size of right. Okay, this is the last thing you need to know. Any questions? I think we are done for today. Let's go to the lunch and then the contest. Yeah.
Left tree will always become root.
No, this is the probability of the left tree to become a root. Like I threw the dice. So imagine I have a random generator that generates some random number uniformly distributed from 0 to some value. So I threw this dice. If it's less or equal than size of L, then I say, okay, left tree is the root. In other case, I say the right tree is the root. Okay, that's all. Any questions? Okay, thank you for the attention. You can have an array where you can what's the advantage
Esse crachá sobrando. Pode calçar. Não, preciso de um crachá extra pra dar pro menino que tá sem. Vai arrumar um crachá pra você.
Está na minha sala.